All right, so good afternoon, everyone. My name is Jesse, and I am with Exploring by the Seat of Your Pants. For those joining us for the first time, we are all about bringing conservation, adventure, and science into classrooms around the world. And we are really excited this month of October because all month long, we are highlighting space. We've got astronauts, engineers, all sorts of amazing people from all around the globe that are sharing their incredible work, their research, their expeditions, and more. And so thank you guys for being a part of our biggest month ever. Right now, we've got 3 classes joining us from across North America, so I'm going to give them a chance to say hi. We got Miss Breeze's class, grade 5s in Canton, Michigan. Their mic isn't working, but they're there. Welcome in, guys. Nice to see you. Oh, their videos isn't working either. We got all the tech issues today. Keeps it interesting. We've got Miss Ouellette's group, grade 6s in Vancouver and BC. Hi, guys. Hey. All right, and then we've got Miss Carol's group, I think grade 5s in Honolulu in Hawaii. It's so nice to have a Hawaiian group involved. Hi, guys. Hey, there's so many of you. All right, the reason you guys are all here today is for our speaker. So we're joined live in Montreal, Canada by Nathalie Ouellette. So she is a science communicator for the James Webb Space Telescope, the upcoming grandest thing we've ever put in space for understanding more about the universe than we've ever seen before. I know we're a little late starting today, so I'm going to turn it right over to her to dive into the amazing work she gets to do and the amazing work that the James Webb Telescope is going to do and beyond. So without further ado, thanks so much for joining us, Nathalie, and take it away.
Thank you, Jesse, so much. So I'm Nathalie. I'm here in Montreal, Canada, and we changed my title slightly. It is now the outreach scientist for the James Webb Space Telescope. That's totally cool. It changed like 3 or 4 times in the last year, so it's hard to keep track. A little bit about me. I am an astrophysicist by training. I finished my PhD in astrophysics 3 years ago. And I have been doing a lot of outreach work since then. So when I was doing graduate work, which is my master's and my PhD before, I ran an observatory on my campus and I fell in love with outreach. I loved talking to people about science. And so I wanted to find a job later on that let me be a scientist, but also let me talk to the public. So that's what I do now. So I do that for a bunch of different things, including the James Webb Space Telescope, but also for an institute where I work called the Institute for Research on Exoplanets. So I'm going to share my slideshow because my face is not as interesting as space pictures. So hopefully everyone can see that. Give me a thumbs up, Jesse, if you can see my screen share. Okay, perfect. All right, so one of the really cool things that you get to do as an astrophysicist is travel a lot. And this picture might be especially interesting for the class in Hawaii right now. This is a picture that was taken on the top of Mauna Kea on the big island of Hawaii. And we have lots and lots of telescopes there. So I've been able to go there and take data, and you get to travel to lots of different places to go to conferences, but also to actually use these telescopes. And so you see the night sky and it's really, really beautiful. Another place I've gotten to go is New Mexico. This is called the Sloan Digital Sky Survey. And it's a pretty special telescope because instead of having astronomers ask it to look for specific things for their project, it just takes entire pictures of the whole sky systematically over and over again, and then puts all of that data online publicly for everyone to access. So that means it's really, really great if you are at a school that doesn't have access to a big telescope, or maybe you live in a country where you don't have a big telescope of your own. You can use that data from like a really good telescope and you still are able to do science no matter where you are in the world. And in fact, there are lots of really cool projects that you can end up doing even in high school using that data. So that's really interesting, and it's really made astronomy science a lot more accessible to just everyone around the world. And probably my favorite trip up until now that I've gotten to go on is in Chile. So this is the VLT, or the Very Large Telescope. Our acronyms are kind of funny in astronomy. We're not very original sometimes. It's a really, really big telescope. It's 10 meters wide. It's one of the biggest optical or visible wavelength telescopes in the world. And it's in a really, really special place in Chile called the Atacama Plateau. It's a desert, very high desert. That means that it's very, very dark, no light pollution. It's very dry, which is good because you don't have a lot of clouds. You don't have a lot of water vapor, which is what you want when you do astronomy. So those are some of the really cool places I've been. I've been to other places as well, but we don't only do astronomy using telescopes on the ground. We also go sometimes in space. So one of the telescopes that almost everyone knows about now that is in space is called the Hubble Space Telescope. That's the one on the left here. It's the one that's sort of silver. And it's been going for almost 30 years now. So it's almost as old as I am, older than all of you guys, I'm sure. And it's still going pretty strong, but it's not going to be able to live forever, unfortunately. So right now we're working on its successor, not what's going to replace it really, but it's going to be able to work in a lot of the same ways as Hubble, but it's also going to be very different. And it's called the James Webb Space Telescope. And that's the really cool looking gold one that kind of looks like a beehive. So it has all of these little mirror segments. It's not like one giant mirror. And they're all coated in gold because gold is very good for reflecting a specific kind of light called infrared light. So if you've ever seen like in a movie, sometimes you can put an infrared camera or you can like put infrared goggles and then like people look like they're glowing or animals look like they're glowing. That's because we're very shiny in infrared light, not so much in like visible light, what we see around us from like the sun and everything. Infrared light is really interesting because it lets you see the universe in a completely different view. So infrared light is what's going to be used in the James Webb Space Telescope, and it's going to be 3 times bigger than Hubble. So we're really excited about that. And it's going to be launched in 2021, and it's a collaboration between NASA, which was also in charge of the Hubble Space Telescope, the European Space Agency, who also had a part to play in Hubble, but really excitingly, the Canadian Space Agency is going to be involved, is involved in the James Webb Space Telescope. And I'll explain some of the things that we do with James Webb. What I study personally is something called galaxies, and there are lots of different kinds of galaxies in the world. So the picture that you see in the center here, this is our own galaxy, but it's not a real picture because our galaxy, the Milky Way, we're kind of like stuck inside of it. And if we wanted to take a bird's eye view picture of it, we would need to shoot a camera up into space, and it would have to travel for a really, really long time to get far enough away to take a whole picture of it. So instead, we use everything that we know, we put it in a computer, and then we try to figure out what we think the Milky Way looks like. And we think it looks like this, and it's called a spiral galaxy. So you can see the spiral arms on it. So that's really good. But there are lots of different types of galaxies out there too. Lots of spirals, and they can have different colors, different numbers of spiral arms inside. And because spiral galaxies and all galaxies are 3-dimensional, that means that you can see them oriented or flipped around in different angles. So sometimes you see them from straight on and they just look like big spirals, but sometimes you see them from the side and they look sort of flatter. And some galaxies are what we call elliptical galaxies, and they don't have spiral arms at all. And usually they're much more red. One galaxy that we can take a whole picture of and that we can take a really nice picture of is the Andromeda Galaxy. It's sort of like the Milky Way's twin. It's our closest neighbor. It's also a spiral galaxy. It's really close by. And something that's pretty interesting about the Andromeda Galaxy is actually that we are going to collide with it. The Milky Way is going to collide with it in about 5 or 6 billion years. So it's a really, really long time, but eventually we're going to collide with it and become only one really big galaxy. And that's not that unusual for it to happen. There are lots of galaxies that collide together because galaxies tend to sort of huddle in these groups, and then sometimes they get really, really close together. And then the gravity between the galaxies make them hit each other. And sometimes we're lucky enough to take a picture of that collision happening. So these are 2 galaxies that are colliding together, and they're like, we're taking like a freeze frame of the collision. But if you were to stare at these galaxies night after night, you wouldn't actually see them moving. These collisions happen over, hundreds of millions of years. They take a really, really long time. And it's not because the galaxies are moving super slowly. They're actually moving really fast, but they're just so big and space is so big. It takes a really, really long time for all of these collisions to happen. And one of the types of galaxies that I am the most interested in is galaxies that are found in groups called clusters. So I mentioned that galaxies like to be in groups, and the Milky Way is in a group of about 50 or 60 members, but I work in a group called the Virgo Cluster, and that has over 4,000 galaxies in it. So here we have in the background a picture of the Virgo Cluster, and you see all the little dots, almost all those dots that you see are galaxies. There's like lots and lots of them. And you can see a close-up of a few of them here. And what I really like about the Virgo cluster is that it's far away, compared to, say, Andromeda, and there's lots of things in it, but it's still close enough that I can take a nice picture and I can still see that it looks like a galaxy. So you can see in some of the close-up shots here, you can see a little bit of the spiral arms, you can see some structure inside of these galaxies. So I really like trying to figure out how these different galaxies interact with each other. And I also study something that's really mysterious that's inside of these galaxies called dark matter. So if you're interested in finding out more about dark matter, you can ask me a question about that later. So that's what I do in my research. But because I work at the Institute for Research on Exoplanets at the University of Montreal, I am surrounded by people who work in something completely different and that I'm working and learning more about every day, and that's an exoplanet. So you might know what a planet is. We are in a solar system and we have 8 planets, including the Earth, in the solar system. We have 2 types of planets. We have the rocky planets, which are Mercury, Venus, Earth, and Mars. And we have the gas giants like Jupiter, Saturn, Uranus, and Neptune. But these planets are just, these rocks and gassy worlds that orbit around a star, the sun. But there are lots of stars out in the universe that are not our sun. And for a long time, for hundreds of years, people have looked at the stars in the sky and wondered, well, we have planets around our star. Why can't those stars have planets around them too? So we started thinking maybe there are other planets out there, and we gave them a name and we called them exoplanets. So here you get to learn a little bit of French, maybe. It's the description is written in French. It says, planète qui tourne autour d'une autre étoile que le soleil. That just means a planet that turns or orbits around a star other than the sun. So exo means outside of our solar system, and planet is just planet. So exoplanet is just a planet outside our solar system. That's it. And even though we've been thinking about these worlds for a long time, for hundreds and hundreds of years, we've only just recently been able to detect them for the first time. And the first time we detected a planet around a star that sort of looks like our sun was in 1995. Now, maybe to you guys, 1995 sounds like forever ago. But 1995, I was already born and I was already, interested in astronomy. And a lot of people actually were studying something else in astronomy. And when this big discovery happened, they were like, oh my God, there are these worlds that we can discover and study now. I'm going to switch fields completely. And so this first exoplanet detected in 1995 is called 51 Pegasi B. The little b means that it is the first planet around the star that we found. The star is 51 Pegasi. And then when we find an exoplanet around it, we put a little lowercase b. If we found a second exoplanet, we would call it 51 Pegasi C. If we found a third one, it would be 51 Pegasi D, et cetera, et cetera. So this is the first time, as I mentioned, that we discovered a star around a sun, a planet around a sun-like star, but it doesn't look anything like the types of planets we have in our solar system. It's actually really, really weird. It is a really big gassy giant, about half the size of Jupiter, but it is really close up to its star. So in our solar system, the planets that are closer to the sun orbit very, very quickly around the sun. So Mercury is the closest, and it only takes 88 days for it to go around the sun. Jupiter's farther away, and it takes something like 15 years. It goes a lot more slowly. It's much farther away. 51 Pegasi B, the first exoplanet, takes only 4 days to go around its star. You can actually see here, if you look at the orbit of Mercury and you compare it to the orbit of 51 Pegasi B, it is way closer to its star than Mercury is to our sun. That's how close it is. So we call this kind of exoplanet a hot Jupiter, because it's like a Jupiter, really big, but because it's so close up to its star, it gets really, really hot. So that was the first one. And as we got more and more interested in exoplanets, we started building different telescopes and different instruments that can study and find these different exoplanets. We even built a telescope that we sent to space called Kepler in 2009, and its only job was to find exoplanets. And by itself, it discovered 2,700 exoplanets, and it wasn't even looking all around the sky. It only looked at one region of space that is about the size of the palm of your hand if you hold it up to the sky at arm's length. So in that little piece of the universe of our sky, we found almost 3,000 exoplanets. And that was just one telescope who did that. Now, we are still finding lots and lots of exoplanets. Kepler took took a break. It's retired now, but it got replaced by a new telescope 2 years ago called TESS. And TESS is finding lots of exoplanets too. And right now we know of about 4,200 exoplanets. And you can see here a picture of some of these exoplanets. These are all drawings because it's very difficult to take real pictures of exoplanets. You can sometimes take a picture of an exoplanet if it's really big and really bright and far away from its star, but it doesn't look like this, unfortunately. It's more like a bright dot in the picture that you're taking. But in all the exoplanets we've discovered, we found some that are big like Jupiter and gassy. We found some that have rings like Saturn. We found some that are smaller and could be rocky like the Earth. We find some that look like all different kinds of planets. And a lot of the ones that we're finding, we don't actually have a planet in our solar system that look like them. Some of them are ocean worlds where you have like a rocky core and the entire core is covered by an ocean that is hundreds and hundreds of kilometers deep. And one of the things that we would want to answer at the Institute for Research on Exoplanets is, are any of these worlds, these alien worlds, inhabitable, meaning that there could be life on them? And that is one of the things that the James Webb Space Telescope is hoping to do, is to study these planets, study their atmospheres if they have them, and try to figure out if there are really important things in the atmosphere for life, like oxygen or water vapor, or if there are even what we call biosignatures, which are signs of life on these planets. So one of the things on Earth that we can see in our atmosphere that is a sign that we have life here is sometimes pollution or carbon dioxide, and something called methane, which happens when, you know, a cow farts or when you fart too. So we're actually looking for stuff like that in these exoplanets with the James Webb Space Telescope. And so we're a really big team at IREX working on that. We're working on the James Webb Space Telescope, but also lots of different telescopes that go on instruments that go on telescopes on Earth as well. We're about 45 members now, students all the way to professors, and we do lots of outreach things as well. So I'm in this really interesting place now where I study galaxies for my own research, but I also work a lot with exoplanets for the other half of my job. So I get to talk about space and study space and all kinds of different things in space, and I get to travel a lot. So I really, really love my job, and doing stuff like this is also one of the big perks. So I hope that gives you sort of like a sense of the different things that I get to do, the different things I get to study. And now I am happy to answer any questions you might have.
Outstanding. Well, thank you so much, Nathalie. That was marvelous. And in addition to our live classes, we now have 8 classes watching on YouTube. So if you guys want to type in questions, please do pass them on there. I'll share them with Nathalie. So that's fantastic. And some of you already are. But yeah, let's dive in. We'll head to Honolulu first. If you guys have a question to kick us off, come on up and go for it.
Okay, you gotta come close. Come nice and close. Okay, we're coming.
Take your time.
First, right here, and just say your name, your first name.
I'm Dylan. And what is dark matter?
Okay.
Ooh, let's start with the hardball one. Go
That's right. Good stuff. All right. So we don't actually know what dark matter is. That's still a really big mystery. But we know what the effects of dark matter is. So the way that we discovered this, there's this thing we call dark matter exists in the universe. We were looking at galaxies, and we were looking at how fast stars were spinning on the outside of the galaxy. And so the speed at which something is spinning around a galaxy or a solar system, it tells you how much stuff is inside of that galaxy. So for example, we can measure how massive the sun is in the solar system by looking at how fast the planets are going around it. So it's the same thing for a galaxy. We are looking at how fast the stars are spinning around the center of the galaxy. So when we did that, we calculated how much stuff we needed inside the galaxy for stars to be spinning as fast as they are. And then we counted up all of the bright stuff that we saw inside the galaxy. And when we compared the two, we realized that there was like a lot of missing stuff that wasn't bright. So we called it dark matter, or, you know, it's dark stuff. Essentially, it doesn't create light. It doesn't absorb or reflect light. It doesn't, you know, interact with light, but it interacts with stuff gravitationally, which is why it's making the stars move around really fast. And there are lots of different ways other than that we discovered that dark matter exists. But right now we can see its gravitational effects, but we can't figure out what it is yet. And so there are lots of different teams around the world, not only astronomers, who work together to try to figure out what it is. Astronomers look at its effects and try to figure out, okay, what stuff could be there that would react like that would make gravity act like this. And then we talk to people who are particle physicists, and they create these really big detectors who try to detect the kind of particle that we're looking for. And often those people are putting these detectors in like really weird places like mines. So there's a really cool mine called Snow Lab in Sudbury, Ontario. It's 2 kilometers underground. And they built like this giant ball filled with a liquid who would interact with what we think are dark matter particles. But we still haven't detected a dark matter particle yet. But we're getting pretty close. But we have to build these detectors to be bigger and bigger and more sensitive, because the particles are very hard to detect. They don't tend to interact with normal stuff very much. So that's what we know about dark matter now, but it's still an open question what exactly dark matter is.
Yeah, great answer. And by the way, I really appreciate that question coming from a grade 5 class. It used to be that it was like grade 10s and 11s. Now it's like just going down.
Yeah.
And we're doing a session with Snow Lab later this month. So if you guys are keen to see all
Awesome.
about that lab, it's fantastic. All right. So Miss Breeze's class, I don't know if your mic's working, so I'm going to unmute you and see if it works. And if it doesn't, then you can type in questions at the bottom. Let's see. Can we hear you guys? I don't think so. So smack it or sign out and sign in again. Smacking the computer does work 9 times out of 10, but you can type your question in the bottom, little chat bar oval with 3 dots in it. So type them in there and I'll pass them along. In the meantime, we'll go to Vancouver. You guys have a question? Come on up. Miss Ouellette's class. Hey guys. Oh.
Wait, can you hear us?
Yeah, we can hear you. You're great.
What is the sun made of?
What is the sun made of? Yeah.
What is the sun made of? So the sun, I don't have a picture of just the sun, but we sort of know what the sun looks like when we take a picture of it, not from on the earth, because the sun doesn't look at all the same when you're, don't ever look at the sun. But if you were to look at the sun from the earth, it's just very glary. But when you see it from a telescope in space, it's like a really big orange ball that looks like it's on fire. And the big majority of the sun is made up of what we call hydrogen. Hydrogen is a gas. And the gas is really hot on the surface. It's about 6,000 degrees. And as you get closer and closer to the center, it gets close to like 1,000,000 degrees there. And it's so hot that it's sort of like, it's almost like it's on fire. And something that happens in the heart of the sun is something called nuclear fusion. And so hydrogen is the most simple element that we have on the periodic table. It's the most simple chemical element. And it's like, a big ball at the center called a proton, and there's like an electron around it. And sometimes you can take those balls, and if it's like they're really crunched up together, you squeeze them together and you fuse them together. And that nuclear fusion produces energy. And when you produce that energy, well, number one, you're heating up the sun. The sun is producing energy and, keeping its warmth and giving all of that warmth to the other planets. But that turns that hydrogen into the next element called helium. So there's a little bit of helium as well inside of the sun. And then if you keep going down the periodic table, there are some of the other elements like beryllium, and it goes all the way down to iron. But they get more and more frequent as they get older because more and more stuff got fused. But for the most part, for the longest part of the life of the sun, it's mostly hydrogen.
Outstanding. You guys are learning a lot of really neat stuff you're not going to learn in school for like another 5-10 years. So get excited. Ms. Breeze's class typed in their first question, which is, why don't you send a satellite to find an exoplanet? You hinted at this earlier, but I'm really glad we got a follow-up. So why can't we send something to an exoplanet?
Yeah. So the exoplanets, we're starting to be able to detect them for the first times for the last few decades, because our technology is getting really good, because our telescopes are getting great. Our telescopes have like really good eyes. They can see essentially. So an exoplanet is sort of like trying to see a little firefly that passes in front of a giant lighthouse. If you are like in Montreal and the lighthouse is in like Vancouver, It's really hard. So the telescopes are super good. They have like really good eyes. But if we want to send like a spaceship or a rocket to find these exoplanets, that's a lot harder because it takes a really, really long time. Things are very far apart from each other in space. So if we take, for example, the sun or even inside the solar system, if we wanted to send something to Mars, that would take at least 8 months. And that's only if we time the orbits so that the Earth and Mars are like really close together. If we want to go outside the solar system, things get a lot worse. So if we compare the sun to its closest star, which is called Proxima Centauri, it is what we call about 4 light years away. Now, a light year is the distance that light travels in 1 year. And trust me, that's like in kilometers, lots and lots of zeros. It's a very, very far away distance. So if, and we're lucky because it just so happens that that star, Proxima Centauri, has an exoplanet around it. We detected it, but there was not a guarantee that that was going to happen. If we wanted to go to that exoplanet and we used the fastest rocket ship that exists right now, it's not even made for humans to fly on it, but it's the fastest thing. It would take 7,000 years for that rocket ship to reach the closest exoplanet. And most exoplanets are like way, way farther away. So if we wanted to reach those exoplanets, it would take hundreds of thousands of years. So we're better off building telescopes with really, really good eyes instead.
Since it's hard to keep some science funded for like 2-year periods, a 7,000-year mission might be a bit
Yeah.
Great answer. All right, we've got a bunch of questions from classes on YouTube, so I want to pass them along. We've got a class, homeschool in Manchester, New Hampshire, Ms. Sarwalk, and she wanted to ask, when was Hubble made?
So Hubble was launched in 1989, if I remember correctly, maybe 1990. It's like around that period. But it was actually being built for like a long time before. So something that's interesting about these space telescope missions, they take a really long time to build. So you can't just like decide, okay, next year I'm going to send up a space telescope, and then you like get a group of friends together and you start gluing stuff together. They started working on Hubble like it's at least as an idea in the 70s, and then they were building it in the 80s. And it's the same thing for James Webb. The idea of James Webb, it had a different name at the start. It was like the Next Generation Space Telescope, I think. They started thinking about that in the 90s when Hubble was sort of just starting up. And Canada became involved in like the year 2000. Initially, when we started, when we got involved in 2000, the launch date was in 2008. But we realized we needed more time. We needed to build a telescope that was like more tested, more robust. And that's why now the launch is in 2021. So Hubble was launched in like 89 or 90, but it was an idea much longer before then.
Outstanding. All right. Question from Miss, where's our next question? Miss DaCosta's class, grade 5s in Crystal Springs. They wanted to ask, do you use physical models to study space?
Yeah, so there's actually a field called astrostatistics now, where you have astronomers that are also trained as statisticians. And for the longest time, astronomers had to use statistics because usually when we're studying a type of object, whether that be a galaxy or a planet or a star, we study lots and lots of them because we don't want to just study one separate galaxy and then it has these characteristics, and then we don't necessarily know if everything looks like that. So it's sort of like trying to figure out what is an elephant like. You can't just study one elephant, you have to study hundreds and thousands of elephants. It's the same thing in astronomy. And when we have lots and lots of data like that, we have to learn some statistics. And for the longest time, we did that. We learned like sort of the minimum amount of statistics that we needed to just to get by. But now in this era, we have telescopes whose entire point is to do a census of the entire sky every few nights. So I talked about the Sloan Digital Sky Survey a little bit. That's a telescope that I visited in New Mexico. Its replacement is going to be called the Large Synoptic Survey Telescope, or LSST, in Chile. And every single night, it's going to take 1/3 of the sky in pictures. And so that's going to be so much data that we have to start hiring data scientists who, you know, they write algorithms, and they even have to start dabbling in machine learning and artificial intelligence to try to like look at all of this data. So statistics is becoming more and more important in astronomy. And now you have astronomers who specialize in statistics.
Very cool. All right. We're going to dive back in and go to Honolulu twice in a row. I know you guys need to leave at 2:45 Eastern, so I'm going to take 2 questions from you guys back to back, and then we'll go back to the other classes, okay? So yeah, come on up.
All right,
I
we'll just
I like the willing arms, just like, you know, make him go faster. All good. Perfect. Go for it, man.
question.
So my name is Damien Din, and how does the liquid that they use to detect that they're supposed to detect the dark matter particles work? How do they work? Like, in the ball?
All right. So the liquid inside, it depends on the different detector, but usually it's filled with a liquid that doesn't react with sort of normal matter in general, but it tends to react with certain particles that have a certain amount of energy. So this is sort of like where people who work in particle physics need to go through their theory. They have like this graphic where they decide, okay, we think dark matter exists in this region, so it has to have this size, this mass, this amount of energy, and they decide what kind of liquid would interact with that kind of particle. So then you have a really, really big vat filled with this type of liquid, and then you try to make sure that you're in a really, really clean environment, a clean room where there are no unwanted particles that are, you know, floating around from other things going on. So you have to make sure that everything is very clean. There's no radiation anywhere around you. And you wait for, hopefully, a dark matter particle to come through and interact with a particle of the liquid. And when that happens, there'll be like a little burst of light that happens. And the inside of the detector is covered in what we call photodetectors. So they are super, super sensitive, and they detect that tiny little flash of light. And then they try to study exactly how bright that flash of light was, what the orientation of it was, to try to figure out what the particle that caused that flash of light was. And hopefully it's a dark matter particle. So it causes a flash of light that you can then study to figure out the particle that you just detected.
Very cool. All right. And a great explanation. I've never heard that explained that way. All right, back to Honolulu. Come on up.
So I don't know if you know this, but on Mauna Kea, we're thinking about building a $2 billion telescope called TMT. And there's a lot of controversy surrounding it, whether it's like on native land or will it benefit the Society of Astronomy? And I was just wondering what your point of view on that was. Thank you.
Great question.
Yeah, so I'm very familiar with the 30-meter telescope. Canada is actually part of that group, that collaboration right now. It's a really, really hard question because I think the TMT, the people, the astronomers, they mostly have good intentions. They're just hoping to do science. Mauna Kea is a really special place for lots of different reasons. It has a lot of cultural significance for Native Hawaiians. Scientifically speaking, it is the best site in the world for astronomy because the sky is very, very dark there and the air is very still. So if you want to take clear pictures, there's no better place in the world. But at the same time, science at the detriment or going against, you know, the good of society is not good. You want the two things to work together. So the TMT, I think, tried to plan for the construction of the telescope in the sort of normal legal route. They went through the courts, they got the permits and everything, but maybe they didn't have quite enough conversations with people in Hawaii. And when they started doing that, maybe it was a little bit too late. So my take on it is essentially, there were some mistakes that were made pretty early on, and it's hard to go back and erase those mistakes. And now my opinion is that it should be left in the hands of Hawaiians to decide because it's your land essentially. And you're the ones who are going to live with the costs and the benefits of the telescope. The telescope would potentially have lots and lots of good sides to it for Hawaii. Economically, it would create a lot of jobs. There's a really strong culture of astronomy already in Native Hawaiian culture. They use astronomy a lot for navigation and everything, but at the same time, it's not our place to make a decision what happens on your land. So we want to be there if you want to invite us in, but we don't want to force ourselves on the native Hawaiians and the Hawaiians in general. So Canada's stance in general is to really leave it in the hands of Hawaiians, and we don't want to impose.
That's a very thoughtful answer, and I'm really, really glad we got that question. I thought we might with a class joining in from Hawaii, and so thank you so much to that student for coming up and asking that. That's fantastic. All right, a question from Miss Breeze's class. Again, their audio is not working. We apologize for that. But we've got, have you seen a black hole? Have we seen black holes?
Yeah, so for the longest time, well, for a pretty long time, we've seen, sort of like dark matter, the effects of black holes. One of the really cool ways that we saw the effects of a black hole was when we were looking at the center of our galaxy. We saw that there were stars very, very close together near the center that were orbiting very quickly around nothing. There was nothing at the center there, but they were like spinning around super fast. And like I mentioned, when you're looking at something orbiting or spinning around, you can sort of tell the amount of stuff inside its orbit that needs to be there in order for stars to be spinning around that fast. And there was like a lot of stuff there. There was like millions of times the mass of the sun, but we couldn't see anything. That's when we realized that there was a black hole there at the center of our galaxy, and not any kind of black hole, a supermassive black hole, many millions of times the mass of the sun. And that's what was causing these stars to orbit around the center of the galaxy so fast. But we didn't have a picture of the black hole. We only had an image of the star spinning around, so we saw the effects of it. Up until April of this year, where finally we took a real picture of a supermassive black hole. Not the one at the center of our galaxy, but the one at the center of a galaxy in the Virgo Cluster that I study. It's a galaxy called M87, and that supermassive black hole is billions of times more massive than the sun. It's really, really big. So we took a real picture. The center of the black hole, because it sucks in light and the light can't escape. It has a shadow. So the center is like a shadowy, mysterious black circle, but we can see around it what we call its event horizon. And that's where all the matter, all the stuff is falling into the black hole, and it's falling in pretty fast. And all the particles as they're falling in are rubbing together. And if you rub your hands together, your hands will get warm. So it causes the particles to rub together and start glowing. So that's what you see around it. So that was the first time we ever took a real picture of a black hole. And that was not an easy picture to take. They used a big network of 8 radio telescopes on Earth that simulated essentially a telescope the size of the Earth. So a really, really big telescope in order to see enough detail to take a picture of the black hole. And we're hoping that that's just the start. And one of the next things that they are wanting to do is take a picture of the supermassive black hole at the center of our galaxy.
Very cool. All right, we're going to take 3 more questions, 2 from groups on YouTube, and then finally we're going to wrap up with Miss Ouellette's class. So first, Miss Egdahl's class in Forest City, Iowa wants to ask, how does the Earth move around the sun and not just float off? Which is a great take on gravity. I like it.
Yeah. So it's because of a force called gravity. So the same force that causes all of us to not float off into the air, into the atmosphere, and instead stay our feet on the ground, that's what keeps all of the planets, including the Earth, sort of spinning or orbiting around the Earth, around the sun. So any kind of mass will change the shape of what we call space-time. So space-time is sort of like a big rubber sheet where we're all living on. And if you imagine the solar system like a really big rubber sheet, you have a really, really big mass at the center called the sun, which is changing the shape of that rubber sheet. So imagine you have a rubber sheet and you put a bowling ball at the center. So then you have like this divot that is created by this big bowling ball, and you have all the planets that are sort of like not on the flat part of the rubber sheet. They are on the inside part, the divot of the rubber sheet, and they never change the amount of energy or the speed that they have. They have the same amount of energy. So they stay inside that divot along an orbit. In order to escape that hole in the rubber sheet, they would need an extra boost of energy to get kicked out. So that wouldn't really happen unless, we had like giant rocket propulsors on the Earth and tried to blast off, or we had something hit us essentially. But that's essentially why we can't get out, because we're stuck in that divot caused by the sun that's warping the rubber sheet of space-time.
Very cool. All right. We've got a question from Mr. Bassus's group at Richmond Hill High School. So it's a two-part question. They both go really long, but they're great questions. So for finding alien life on exoplanets, what are the ideal biosignatures we're looking for? You might have to explain what a biosignature is to our classes. And then the follow-up to that is, do you believe alien life exists? Of course it was going to come.
Yeah, so some of the biosignature is a kind of element that we would find inside of an atmosphere that we would be studying on an exoplanet that is a sign of life, essentially. So one of the experiments that we did actually was to try to figure out, if we're out in space and we look at Earth, can we see signs of life? We're on Earth, so we know that we're alive and we know that there's life on Earth. But we sent out a probe to Jupiter at some point called Galileo, and Galileo at some point turned around, used its instruments, and studied the atmosphere of the Earth and tried to see what the biosignatures for Earth was. And we found things like carbon dioxide, which, a lot of it is pollution, and water vapor and oxygen, which are things that we need, not biosignatures so much, but things that indicate that at least it's a livable place. And something that's really interesting for a biosignature is ozone, which is what protects us from the sun, and methane, which is, as I mentioned, cow flatulence, but all living creature flatulence. And something happens where certain ratios of those molecules can only exist if you have something on the planet that is constantly producing them. Because otherwise the molecules will react together chemically and they'll transform into something else, or one type of molecule will be completely destroyed and then you only have the other type. To find a certain ratio of those molecules means that something is constantly producing them. Something is constantly farting on Earth, essentially. So not only the biosignatures like ozone and methane are important, but the ratios can tell us a lot about if something is constantly producing those biosignatures. And if I believe in aliens, so it depends what kind of aliens you mean. So if you mean little green men that potentially have visited us, I don't have any reason to believe that that's the case. It could be that at some point in time, there was intelligent life like us that could communicate with radio signals, and maybe in the future there will be. But when we think about humans, we've only been able to sort of communicate long distance with radio waves for a little over 100 years. It hasn't been very long. And the universe is 13.7 billion years. So a little civilization, the time that it can communicate with another civilization is like a tiny blip in the history of the universe. So it could be that there have been other blips of civilization, but they've never been timed at the same time where the blips can talk to each other. So maybe there have been alien civilizations, but there are none right now, and then humans will maybe die out before the next one is created. But I do think that there are probably alien bacteria that live at the same time as us right now on an exoplanet, maybe not that far away, relatively not that far away, and that's what we're looking for.
Well, and out of curiosity, so you mentioned the fact that, if you've been communicating for 100 years, so they could exist at the same time, because if they sent their messages and they're 100 light years away, it wouldn't have even reached us yet. So we could have things to the other side of the universe that are existing now. They're just too far away, given the scale.
That's right, exactly. The universe is a really big place, and the universe has lasted such a long time. It's hard to get the timing just right to talk to each other.
Yes, but you're saying you don't think they built the pyramids.
Yeah. I don't think that, and I think I'm like the ancient alien guy that's like slowly getting abducted during all of his interviews.
That's the worst. All right, we'll wrap up with a question from Ms. Ouellette's class. Thank you guys so much for your patience today, and this has been fantastic. So come on in Vancouver and wrap us up.
I'm not if you could go to an exoplanet, which one would you go to?
Ooh.
If you could go to an exoplanet, which one would you go to?
Okay, so if I could go to any exoplanet, which one would I go to? And I'm assuming I could just teleport there. I wouldn't have to wait thousands and thousands of years on a rocket ship. One exoplanet that I'm particularly interested in is an exoplanet in a system called TRAPPIST-1. TRAPPIST-1 is super interesting because it's a star that we discovered 7 exoplanets around. 7 is a lot. 7 is almost like a solar system. And 3 of those exoplanets are in what we call the habitable zone. That means that liquid water can exist on those planets. So already it's like a really good candidate for potentially having alien life, and it's something that we want to study later on. Like for James Webb, it's going to be one of the first things that we look at. And one of those planets that are in the habitable zone that could have water is what we call tidally locked. So you might have noticed that the moon always has sort of like the same face in the sky. And that's because it is rotating exactly on itself, exactly at the same rate as it orbits around the Earth, so that it's always pointing the same face towards the Earth. We can never see what its behind looks like. We only look at its front. And the same thing exists for one of these planets on TRAPPIST-1. It always has the same face that looks at the sun. And so that it's always daytime on one side and it's always nighttime on one side. It doesn't spin around so that there's, like daytime half the time on one side, etc. So we think that on this particular one, there's probably liquid water, but it only exists like right on the border of nighttime and daytime. So there's like a ring of maybe liquid water along the poles like this. And so I think that world sounds really, really funky, where, what we call the terminator, which is like the limit between night and day, has this liquid water ring around it. So I'd be really interested in looking at what that planet looks like, that exoplanet looks like.
Very cool answer. All right, Nathalie, before we wrap up, I just wanted to ask, is there anywhere you can guide students to learn more about the work that you do, about the James Webb Telescope, about anything that you find particularly fascinating in space, and then we'll share them with the classes through an email?
Yeah, so exoplanets.ca is the IREX website. And so you can find out more about our team, you can find out more about our projects. And if you ever happen to be in Montreal, we have lots of public events there where we put all that information there. And I would say if you're interested in finding out more about the James Webb Space Telescope, webtelescope.org, which is run by Space Telescope Science Institute in Baltimore, which I work with them a lot, is a really, really good website that tells you about the James Webb Space Telescope, but also all the cool science it's going to do. Oh, and astropanda.space. That's my website too.
We'll be sure to pass that along. That's awesome. Nathalie, this is marvelous. Thank you so much for joining us. We always have the classes demute their microphones and say a huge thank you. So we've only got one class with a working microphone today, but Miss Ouellette's class, if you guys could join us and say a huge thank you to Nathalie, that would be fantastic. Thank you so much for joining us. All right. That was great. For our class, guess I didn't get it. That's okay. For the classes that are joining us, thank you guys so much. For the classes on YouTube, it was fantastic. Thanks for the questions. And Nathalie, you're welcome back anytime. That was marvelous.
Thanks for having me.
All right.